There's another seat here if you want to move up. It's up to you. So we should, yeah.
Yeah, we're supposed to work this out.
Okay. This is like a demo day. So we've been covering, some of you have noticed that we've been covering a lot of chapters. These are sort of introductory chapters. We're going to slow up. We're about to slow up with the rate of chapters per week.
Our rate of change.
Pardon me?
Slow up our rate of change.
Yes, that's right. The chapter velocity. Okay, so we're going to now start dynamics, and we're going to begin where it begins, and that's Newton's laws of motion. There are 3 laws, as you may know. And the goal here is to be able to predict motion given forces, and we'll talk about what forces are. But the idea is that given forces on a body or more than one body, we should be able to predict how the system evolves in time. Before we assumed constant acceleration, right? But there was no dynamics or that was just kinematics. So that's the goal here. So we're going to begin, of course, with the first law. And this deals, you'll see what the point, I'll explain to you the point that Newton was making. Newton was subtle, okay? So we want to consider the special case here of no forces, no external influences. So you go out into deep space and you have a body, right? Some body like this, some object. And if you release it from rest, what's going to happen? Yeah, it should just stay there. We're gonna see that that's not always true, but don't worry about that right now. You have the right intuition. It's gonna just stay there. What if I push it and give it an initial velocity? What do you think it's gonna do?
Stay there.
Yes, it's gonna move with constant velocity. So the situation looks something like this. So can we achieve this? We have achieved this in here. Remember the glider on the air track, right? For the case of a horizontal air track. In this case, there's effectively 0 net force here because there's going to be the force of the Earth on the glider. That's also called the weight of the glider. But then there's a force of the air track upward, and those 2 forces balance. So this is a way of achieving or mimicking this situation here. So here's, and remember, one of the first things we did was I gave the glider an initial velocity, and what happened? It moves with constant velocity. And we checked that with the photo gates, remember? Okay, so here's a statement of Newton's first law. If the net force on a body is 0, the body moves with constant velocity. And that constant velocity could, of course, be 0, right? 0 is a constant. All right. So, but there's a very important caveat, or what's another word for caveat? I had one last night when I was looking over. There's I know what the word is. It's qualification. We need to qualify this. That's, I think, the appropriate word here. But everyone seems to know what caveat is, right? It just keeps coming up every once in a while. So everyone knows. Okay. So here it is. You can't apply this law in any frame of reference. Okay? What if I'm on a merry-go-round? Do they still have merry-go-rounds? Or are they considered unsafe? So you go to parks these days, and a lot of old parks, a lot of rides, apparatus are disabled because they're considered unsafe. Go to Dennis and Menace Park. Last time I haven't checked in years, but you guys noticed that? Yeah, they've taken all the fun away from it.
Still good parks it up.
Pardon me?
They put a fence now around the train. They put a fence around the train so the kids can climb on it.
Oh, did they really?
If you look at pictures of it.
Oh, see, I didn't know. That's been done in the past. Well, I don't know when the last time I checked Dennis the Menace. Maybe been a decade. But yeah, the train was great. But it's potentially dangerous. But that's you. know.
Or being a kid.
Yeah, that's part of being a kid. The problem is people are worrying about that one incident where some kid's going to just really injure himself a lot. Okay, why? How do we get into that? Right. So a merry-go-round, and imagine you got this object, and you put it down on you're on this merry-go-round, and you put it down on the surface. Assume it's frictionless surface, of course, like this. This is approximately frictionless. What's going to happen if I release it from rest? Oh, it's gonna in my frame of reference, it'll appear to move. It'll depart the merry-go-round, right? Can you guys see that? Okay, so the problem there is that's an accelerated. It's accelerating relative to the Earth. It's an accelerated frame of reference. So we have to deal with, in some sense, frames of reference that aren't accelerating. But then you can wonder, accelerating with respect to what? Okay, well, it's a bit of a problem. So I'll tell you how we can get around that. But let me state here before we go to the next slide that, and this is going to sound like circular reasoning, but Newton's first law applies in frames of reference, special frames of reference that we call inertial frames. And if you find that one inertial frame, you can find infinitely more other. All frames moving with constant velocity relative to that frame, they're going to be inertial frames too. Okay, so you may wonder how we, so how do we define an inertial frame? Well, I think Newton understood this, but he didn't want to advertise it too much. He didn't like criticism, and he came under a lot of criticism. So he kind of stayed away from it. But nowadays what we recognize, and again I think Newton recognized this, is that the first law is really a definition of inertial frames. You got to be logical here, you got to turn the tables, and you can't say this, because we don't know what an inertial frame is. So we use the first law to define an inertial frame. If you're in a frame of reference and you want to know if it's inertial or not, one of the first things you're going to do is you're going to release this from rest and see if it just stays there. Okay? And you'll probably have to do some tests in all three directions. I haven't really thought about that. But you want to a body with no net force on it should move with constant velocity. So the first law is really a definition of inertial frames. Empirically, in practice or experimentally, we find that an inertial frame is one in which, if you look out at all the distant galaxies, they're moving outward from us. Okay, if you look out and you see the galaxy spinning around you, you're in an accelerated frame. Now, the Earth is not technically an inertial frame because it's spinning, right? But usually this effect is small. It's not small when it comes to hurricanes, the formation of hurricanes. It's important there, but that's on a very large scale. That's on a large scale compared to other, like demonstrations in this room here. Not only is the Earth spinning, but it's revolving about the sun. So it's non-inertial. It's a non-inertial frame of reference due to that. What's the sun doing? It's going around the center of the Milky Way. And what's at the center of the Milky Way was finally discovered? A supermassive black hole, which is true for a lot of galaxies. What about our galaxy? Is it just sitting there? Our galaxy is part of something called the local group. It's a group of galaxies, and it's going to be, they're gravitationally interacting and they're rotating about some center of mass. Maybe there's a really super black hole at the center of, I don't know, I doubt it. I think it's just galaxies. Okay, now there's a kind of addendum or addition to the first law, and that is this, and you've probably heard this before: a body tends to remain at rest or move with constant velocity when a force is applied. What we're really saying there is that you can't change the velocity of a body instantaneously. If it starts from rest and I exert a force on this, it doesn't just immediately develop a velocity. It has inertia. It has this kind of resistance to changing its motion. And it's not just at rest. If it's moving along with constant velocity, and I now apply a force and I want to change its velocity, it's not going to change its velocity instantaneously because it has inertia. And there's a great demonstration of this, an old classic demonstration. Okay, this is a heavy ball. It's cast iron or something, I don't know what it is, but it's very heavy, okay? And I see that I have this, line here, thread here. It's pretty strong. I can't remember what the test pound weight is. But I'm going to do a demonstration. I'm going to do two demonstrations. The first thing I'm going to do is slowly increase the downward force on this piece of wood here, this dowel. Okay? One of these threads is going to eventually break. Which one is going to be?
The top one.
Yeah, right. Why?
Because that's where the most force is being felt.
Yeah, why? You're there. You're almost there. Let me try to explain it. When I exert a force on here, the tension increases in here. Okay, and we'll be more careful about tension later in the course. But you know tension, right? When I exert this downward force, it's greater tension there. It's a force. As I increase it, this force is going to increase. What about the force up here?
So we're starting with holding the ball, so it's going to...
Yeah, so the tension here is going to be whatever there is, it's going to be whatever the force is I'm pushing on here, plus the weight of this thing. So that tension is always going to, if I do it slowly, that tension is always going to be greater. So you expect the top one to break, right? Okay, so let's try this here. Yeah, this is a 40-pound test weight. I probably shouldn't be using this, but anyway. What happened? Okay, it traveled. Okay, so that worked. Okay, the top one broke. Now that doesn't really have anything to do with the first law. Okay, that's just what we call statics. But now what I'm going to do is do this again, set it up again with this. Now what I'm going to do is, I'm going to do it very quickly. To do it really quickly, I'm just going to hit one side here, hold the other side and hit this. So now I'm very quickly increasing the tension here. If I do it quick enough, is this thing going to know I've done anything? No, I do it quick enough and the tension gets big enough, this one should break. And, ouch. Sure enough, it did. Okay, everybody get that? Yeah, that's a great demo. Any questions about that demo? Oh, I need to make space. Okay. What causes inertia? Why does something have inertia? Something's moving with constant velocity, which could be zero. I exert a force, and it resists that change. Nobody knew the answer to that question for hundreds of years. And it bothered a lot of people. I'm sure it bothered Newton. And finally, you guys may remember this. The question was finally answered in just a few years ago. You guys hear about the Higgs boson? Right. So the idea of the Higgs boson is, this was done by Peter Higgs and other people about a half a century before they finally observed it. The idea is that you have some object, let's say, it could be at rest or moving with a constant velocity in a vacuum. Well, we now know, and we've known since the mid-1900s, that there's no such thing as a pure vacuum. And I'm not talking about, not being able to get all the air out. We can imagine removing all the air in some bell jar or something like that, okay? That's not the problem. When we say that there's no such thing as a vacuum, it's due to the existence of what are called virtual particles. These are particles that come into and out of existence continually, and we cannot directly observe them. Okay, you guys have ever heard of virtual particles? So you might say, well, how do you know they exist if you can't directly observe them? Well, there's an abundance of experimental data that can only be explained by these virtual particles. So when something's moving around, there's a continual exchange of virtual particles of the object with the vacuum. They're absorbing and sending, the object is absorbing and giving off these virtual particles, all right? When the object is moving with constant velocity, there's no effect of the virtual particles. But you try to change that velocity, and they come into play. They give you a sluggishness. They are responsible for the inertia. These virtual particles can be observed under the right conditions if you have enough energy, and it takes a lot in this case, and it's concentrated. You can observe them, and that's what the Higgs boson is. So this was something that had been bothering people for hundreds of years. So we now feel we understand inertia. Of course, you have to understand, you have to know quantum field theory to be able to appreciate it. But that's sort of the simple explanation that I gave you. We have a course in quantum field theory called quantum electrodynamics. It's a 4,000 level course here. It's sometimes taught. So, okay, any questions? Do you guys remember the Higgs boson? It was big news, right?
CERN super collider.
What?
Is that what they discovered at the CERN super collider?
Yeah. And there was a very happy Peter Higgs there. He's still alive. He's kind of old. Okay. Second law, right? What is the second law? You guys probably know this. F equals ma. Ring a bell? Yeah. So what's going on there? Well, first we need to quantify force. What do we mean by force? If you try to do this in general, it can be a little difficult. So, we're not going to be real rigorous here. And I don't know if you can be real rigorous, to be honest with you. But imagine a spring. Suppose I have a spring here. It's unstretched. If I stretch it a certain amount, it exerts a force on the end here. It'll be exerting a force this way if I stretch it, right? So that's a force. Obviously, we're going to call that a force. Suppose I apply that force to a mass, where there are no other forces present. I apply that force to the mass. It's going to cause the mass to move, but I keep that same stretched distance there. That's going to be a constant force being applied to a mass. And what is observed experimentally is that the acceleration is constant. Okay? So constant force, really this should be net. There could be other forces here, but as long as the net force, all this object feels, and we'll talk about this in a moment, all this object feels is the net force. It can't distinguish between the individual forces. All that's important for its motion is the net force. So a little thing about units here that we'll need is if you have a 1 kilogram mass, and it's accelerating 1 meter per second squared, the force is defined to be 1 Newton. Okay, that's a Newton. The conversion here is, Newton is a measurement force, so it's in the British system it would be pounds. A Newton is roughly about 0.225 pounds, or there's 4.45 newtons is 1 pound. So it looks like the question of how many newtons in a pound would be answered really easily here. There's 4.45 newtons in a pound. But in a sense, there's another answer. 1. This is a 1 pound note, and there's 1 Newton, picture of Newton on it. I think I actually came up with this demo. Not that I know if I'm proud of it, but anyway. And it's encased in acrylic here. So these haven't been issued since the 1980s, late 1980s or something like that. But it is interesting, The Brits put a scientist on the currency. Have we done that? What? Yeah, it's not clear, right? But Benjamin Franklin is considered the first American physicist. I don't know if you guys know that. Yeah, he was a scientist.
He's super smart too.
Yeah. So, but I don't think he was on there. Well, I don't know, but he did a lot of other things just besides science. So, what's going to happen if I double the force? Take a wild guess. You double the acceleration. The acceleration is doubled. Okay, so the acceleration is proportional to the force. But wait a minute, force is a vector. So we're headed towards a vector. We've got to come up with a vector relationship here. So here's the idea. Force has direction. When I have, if the force is pointing this way, horizontally that way, what's the direction of the acceleration? Obvious. It's pretty obvious. It's going to be in the same direction. So what's natural to think here is that the acceleration will be proportional to the net force and in the direction of the net force. And this is actually an assumption. It can be verified experimentally. But let me show you what the problem here, potential problem here is. Let's say I'm exerting two forces here in general directions, arbitrary magnitudes, arbitrary directions, okay? And I exert those two forces on a mass. It's going to accelerate. It's going to have some acceleration. And it's natural to think, and it's true to extremely good approximation, that if I replace these two forces with the net force, that the mass is going to have exactly the same acceleration as it does when I have these two forces here. So let me say this again. Imagine you have two forces here exerted on an object. It has a certain acceleration. Now go to a different situation. Just one force, but it's the vector sum of these two forces. You're going to have the same acceleration. And this assumption is famous. It appears in a lot of physics. It's called the principle of superposition, right here. We're saying that the net effect here is just the superposition of these individual, it's in a sense a superposition of the individual effects. And you might expect that because it has a name, that it has a name because it's not always true, and you're right. Okay, there are situations where you just can't superpose. You just can't imagine this situation with a force here and this situation with a force here. Add those forces together and get the same acceleration as you would if you had these individual forces. Some examples are extremely strong electric fields. This is where quantum electrodynamic effects, this fancy theory, comes into play. Gravitational fields, if you're near a black hole. And another one that I need to write down there is waves. When you have waves of high amplitude, when you have two waves of high amplitude, okay, you imagine generating one wave. This could be a surface wave on the ocean, or a sound wave, or a light wave in a medium, or even in a vacuum, actually. I generate one wave, and I generate another wave. What if I add these two? What if I have two waves? What if I superpose them? I add them together. Is the resultant wave just the sum of the two waves? Only for sufficiently small amplitude. When you get to high amplitudes, what happens are nonlinear effects occur. So I'm just trying to get across to you here, and probably not a very good way, that this sometimes breaks down. And that's really why it has a name, because it's an assumption, and it's an assumption that sometimes breaks down. But not for us. It's going to be essentially perfectly accurate for us. So here's where we are so far. We have the acceleration is proportional to the net force, and that's true both in magnitude and in direction, right? It has the same direction. So now we have to ask, what about mass? What if I double the mass? I exert a force on a body. I observe a certain acceleration. If I double the mass, what do you think, what's going to happen to the acceleration? It's going to be less, right? And the easiest thing to think is how much less is it going to be? It's going to be 1/2. So if I double the mass, I have the acceleration. Or if I increase the mass by a factor of 10, the acceleration is going to drop by a factor of 10. So we can summarize that by saying that the acceleration is inversely proportional to the mass. If you double the mass, you have the acceleration. All right, so now there's one little more step here. Well, there's actually more than that, now that I think about it. We've got a constant of proportionality. We don't want to deal with proportion. We want to make this exact, right? Quantitative. So let's plug in 1 Newton, 1 kilogram. We should get, by definition of a Newton, we get 1 meter per second. So you can see the proportionality constant here is just 1. This works like itself. We can just replace this proportionality sign with an equal because we've got, for the case of 1 Newton, 1 kilogram, we've got 1 meter per second squared. So the result is Newton's second law. The net force on a body is equal to the mass of the body times its acceleration. So we're going to use this for the rest of the course, right? And the first law will be in there too because of inertial frames. And the third law will be used too. There's one more law we have to talk about. But before we do that, we're going to do some examples. And also, I want to point something out to you. How do we haven't really defined what mass is. How do we quantify mass? Well, here's one way of looking at it. You can take a double pan balance with a bunch of standard masses. These are like a standard kilogram or fractions of a kilogram that everyone agrees upon because the original one is kept outside Paris somewhere. But what if the terrorists get to the standard kilogram? What? Yeah, right, yeah. Okay, so these are masses everyone agrees upon. You can buy them, and if you want to get real precise, you're just going to pay more. Okay, and I balance this thing, and then I just read off what the values usually stamped on here, right? So I can read off what this mass is. So that sounds reasonable, right? There's a little bit of a problem. We're defining mass here. You can only do this because of gravity. In fact, what we're really defining here is what's called the gravitational mass. We know that mass plays a role in gravity, but we've been talking about inertial mass. It's actually a different type of mass. So this bothered people for a while, and very precise experiments have been done, and they find that gravitational mass is equal to inertial mass. They're both the same. So there's no problem. Okay, so any questions before we do, I think, a couple of examples here? Okay, so let's remember the glider on the air track. This is a horizontal or level air track. And let's say the glider is 250 grams or a quarter of a kilogram. We apply a force of 1.5 newtons. Okay, this is the net force. Remember, the gravitational force is being balanced by what we'll call the normal force. Don't worry about that now, but it's the force of the glider, this upward force. And we're neglecting friction, which is minimized due to the air coming out of the air track. So the glider starts from rest. We apply this force at time t is equal to 0. And we want to know what the displacement is after 0.30 seconds. Okay, now, you might think, oh, we've done this before. No, we haven't. Because we've done it before if we were given the acceleration, but we're not given the acceleration here. The information we're given is just the mass and the force and the geometry here. So this is different now. This is dynamics, not kinematics. We can find the acceleration. Once we find the acceleration, we've done that. It's kinematics. So we use Newton's second law. I'm going to take the vector off because this is all one-dimensional here. So I can solve this for the acceleration. It's the force divided by the mass, and I get 6 meters per second squared. So, like I said, once we know the acceleration, now this becomes a one-dimensional kinematics problem. Here's the general equation for constant acceleration, blah, blah, blah. Okay? And we've been through this so many times. It starts from rest. This is 0. You can call this a 0. Okay? And we want to know where it is after 0.3 seconds, so we substitute that into t right here, and we get a value. That's where it is. So the point here, from a broader perspective, is we've defined we've got this physical system. We've defined what's going on. We've got this mass, we've got this force, and we have an initial condition that's initially at rest. We can describe, theoretically, there may be practical issues here, but theoretically we can describe where that mass is, how it's going to move, where it's going to be, and what velocity it's going to be moving at for all time. Right? We can predict the evolution of this system, how the system evolves for all time. That's sort of the basic idea, one of the basic ideas in physics. Okay, any questions about that? Okay, do they still have air tables? Air hockey it's called? Okay. Yeah, we actually have a demonstration air table here, but it's a monster, and I don't think anyone's brought it out since the 1960s or something. I don't know. It's been a long time. But you know the idea. You have this this puck, and it's a two-dimensional air track, isn't it? You know, we have the one-dimensional air track, excuse me, where we have holes. The air comes out. So this is a table where I don't need to explain this to you guys. You know what it is. Okay. So the puck floats on a cushion of air, which drastically cuts down on the drag. Okay? So it's a two-dimensional air track. So let's say that at time t is equal to 0, we exert two forces on this puck. It's initially at rest. It doesn't really matter. It could be moving because we're actually going to just find the acceleration. But let's just assume it's at rest for simplicity. So one force, this is the top view. We're looking down, right? Again, there's a gravitational force, but it's balanced by this force of the table. So we don't worry about those. They cancel each other. So in the y direction, there's 3 newtons. And in the x direction, there's 4 newtons, and and the mass is a half a kilogram. It's kind of a heavy, pretty heavy. It take a lot of air to float that thing. Okay. So, what's the magnitude and direction of the acceleration? Well, we need to find. First thing we do here is find the net force. If I've got a force of 3 newtons here, 4 newtons here, right angles, and you know why I chose 3 and 4, right? Because by Pythagoras, the vector sum here is going to be at 37 degrees counterclockwise from the x-axis, and the magnitude will be 5, because 5 is the square root of 3 squared plus 4 squared. So 3, 4, 5 triangle. So having found the net force, we use Newton's second law. The net force is the mass times the acceleration. And we've got vectors on there now because we don't know the direction. Well, we do. We know that it has to be in the same direction as the force. So we know the direction is going to have to be here. And the magnitude is just going to be of the acceleration is the force divided by the mass, which is 10 meters per second squared. So here's the final answer. The acceleration, which is a vector, is 10 meters per second squared, 37 degrees counterclockwise from the plus x-axis. Yeah?
And you use trigonometry to figure out 37 degrees, or is that given?
No. You had to use trigonometry. All we're given, this is what we're given. In fact, this is everything right here. So you have to recognize that this angle has a tangent that's 3 divided by 4. Or you could use a sine or a cosine, I guess, but the quickest way is to recognize that we're looking for a tangent that has, that's 3/4. Yeah, you got to do that. Good point. Okay, so this is pretty simple. Don't worry, it's going to get more complicated, more interesting.
Of course.
Any questions? Okay, I was not sure what the time. We're okay now. All we got to do is this. We got time for the third. If you call this a demo, which I do, it says lecture demos. We got plenty of time. So we're now going to talk about the third law. All right? And I think it's best motivated by talking about something all of you know about, and that's recoil, right? And we can, and we're going to demonstrate. I'll demonstrate it here. Now, this is. I don't know if you guys can see this. There's a platform with wheels here. Okay, we got 2 of them. You'll see why we have 2. Looks like I need to put some lubricate those, but it'll be fine. And in the past, these classrooms are carpeted here, and we've always done it. It doesn't work well on this carpet. So I finally realized I'd been saving these bookshelves for decades. I finally found a use for them. No, we actually use them for I take that back. I use them for several demonstrations. So I've got planks of wood down here, so this can move more easily. Okay? So the first demonstration, the first recoil demonstration, is a 30-pound medicine ball, they used to call them, or whatever. Okay, it's heavy. And I'm going to get on here and project it this way. And you know what's going to happen, right? I mean, you know what should happen. And I have to be careful here. And I'm going to ask for 2 volunteers shortly for the next demonstration. So you want to be careful here. You don't want to, right? So you can actually kind of, hold on here. Okay, so I'm going to push this thing. Right, I'm initially at rest. The system's initially at rest, right? I'm going to push this thing this way. And you can see I moved back. What's surprising here is how little I moved, right? But I did move. That's the important thing. And we'll quantify this later in the course. But I just want to point out to you, like I said, it's something you all know, that when somebody propels something, they exert a force on it, there is a reaction force. It used to be called a reaction force. Okay? Newton called this person pushing the ball this way, called that, oh, I got it flipped here. Okay. Called this an action. He called the fact that you have recoil here a reaction. All right? And he, I'm getting ahead of the story. Sorry, let me follow the notes here. We'll get back to that, okay? So imagine now that if I asked, we don't need to do this, but I imagine if I did this again, but I asked one of you to come up and put your foot, where's the wheel? Put your foot right here. And I do the demo. What's going to happen? Am I going to move? No. But there is a reaction force. Something moves. What is it? It's inescapable. The Earth. The Earth moves. And every legitimate scientist believes that, okay? And later in the course, we'll be looking at this more deeply, this kind of what's going on here, and we'll quantify it. But there's a reaction force here, and it pushes me, but because I'm anchored to the Earth, it pushes the Earth. Now, you won't be able to measure it. It's so small, right, because the Earth's very heavy. But it's there. Everyone believes that it's there.
But if we had enough people.
So, it's interesting you brought that up. So I came up with this simple idea here. My previous university in the 90s, probably, a long time ago. And I never thought about it. But Luke is right. So here's the question. So here's how physicists think. What if we had everybody in the world assemble on the equator, and then everybody walks in the same direction? What do you think is going to happen? I mean, first of all, what has to happen? The Earth's going to move the other way, right? Because for us to move, we have to exert a force this way on the Earth. So, and we got a lot of people, billions of people, right, doing this. The question, of course, is how big of an effect would it be? We will. Right. We need to. That's probably what the kind of scale we would be talking about here. About when they. Or not just, it's now there's there's a recent correction that was made. You guys hear about that? Yeah. So, it's probably going to be in that scale, but I don't know. But we will be able to calculate that. So I'm going to try to remember that. Maybe put on a quiz. That'd be a good quiz problem. Okay, so there's a secondary another demonstration we want to do. And so for this I need 2 volunteers, okay? And what you're going to do is what's in the diagram there. So I need one more. So now what you guys want to do is carefully get on here, and you can hold the chalk tray if you want. Yeah. And you're going to put your hands out. Yeah, very good. And so I want, let's say first we're going to do 2 demos here. First, Jared's going to push, don't tell me, Eric. Jared's going to push on Eric. And Eric's just going to hold his hands rigid. Okay? So first you push. Okay, all right. Watch out. Okay, now let's do it again, but Eric's going to push and Jared's not going to do it. And you know what's going to happen, but it's good to see. Make sure we have some clearance for the wheels. Oh yeah, you're fine. Essentially the same. The force wasn't quite as much there, but just, you get the same idea, right? Okay, thanks guys.
You know what? I'm for the medicine ball.
So what's the point here? It doesn't, and Newton understood this. And he said, look, the way we view it now is, it doesn't really matter who does the pushing, okay? There's a force here. When one person or both push, it doesn't matter. One person's exerting a force on the other, and that person's exerting a force on this. And Newton said it like this. He said, and so the question is, how do we quantify that? So Newton says those forces have the same magnitude. So it doesn't matter who is actually pushing here. That would be what Newton called the action. And he stated the third law like this: and you've probably heard this, for every action there is an equal and opposite reaction. Okay. Now, once he did this, he set in motion the fact that we now don't need to distinguish between action and reaction. It doesn't matter what the action and what the reaction is. Those forces are equal and opposite. So we no longer distinguish. You won't hear people talking about too often. Sometimes when they want to emphasize what is responsible for the force, like if the person here is pushing, I would say, this could be the action, this could be the action is the force on here. And that this person feels a recoil or reaction force. But normally we don't distinguish. There's no need to distinguish. There's just there are two interaction forces here, and they're equal and opposite. They're always equal and opposite. That's what Newton asserted. That's the third law. So here's the modern way of saying it. For any two bodies, the force of body 1 on body 2 is equal and opposite of the force of body 2 on body 1. We'll use this notation here. F12 means the force of 1 on 2. F21 means the force of 2 on 1. So they're equal and opposite. So if I have an apple, the earth is exerting a force on the apple, right? I let the apple go, it accelerates. We don't normally think of this, but what's the force of the apple on the earth? Equal and opposite, right? And we will see this. We will see this explicitly when we deal with gravitation later in the course. You'll see it in the Newton's law of gravitation. You'll see the fact that Newton's third law is built into there. What about the moon and the earth? The earth exerts a force on the moon, but the moon exerts a force on the earth. They're equal and opposite. Finally, so this is the famous horse and cart paradox. Has anyone heard of this before? It's been around a long time. So here's the idea. This person is trying to get a horse to pull a cart. So yeah, this may go back to, before automobiles. I don't know. It could. So the horse says, no. Why should I try to pull the cart? Because the force that I exert on the cart is equal and opposite to the force that the cart exerts on me. Right? So the net force is 0. So there's no point in me trying to move the cart. Smart horse. So how do you respond to the horse? I missed what?
Feed the horse.
So what's going on here? We've got this cart, right? This person's trying to get the horse to pull the cart. It is true, what the horse says, it is true. The force that the horse exerts on the cart is equal and opposite to the force that the cart exerts on the horse, okay?
Well, actually, the whole time we've been talking about force, where the object's not moving, it's not really a force because acceleration is 0. So there's no force until the cart accelerates, and then there's the force.
Well, yeah, actually, I would say it's, at t is equal to 0, you exert a force. And you instantly have that acceleration. But the velocity, it doesn't instantly achieve a velocity, right? The velocity will uniformly increase from 0, right? So, but I can exert, forces are independent of the motion, usually. Now, there are exceptions like drag, right? The drag force, depends heavily upon the motion, because you can reach terminal velocity, and we'll talk about that in this course. But when we think of forces, we think of them as independent of the motion, and I can exert them at time t is equal to 0, and it's going to cause an acceleration. They don't depend upon the acceleration usually. I don't know if I'm getting at to what your point is.
I just always thought there had to be displacement in order for there to be a force. So there's like
no, you can imagine. Well,
there's like tension and resistance.
Oh, I think I might see. So in the case of the spring, there's displacement because the spring is stretched. Yeah, but there are all kinds of forces. What about the gravitational force? What's being moved there? No, the gravitational force, there's a force on this rod right here due to the Earth. And it involves, and I'm balancing right now with my hand. Those forces exist, and I'm aware of it because I can feel it. So they're independent of the motion, except in some cases like like drag force. They exist, it's an independent concept. So the way out of this is, what is Newton's, so see that the horse is using Newton's third law here, okay? Which is kind of clouding the issue. What we really should be looking at here is Newton's second law. What does Newton's second law say? Look at the cart. The force on the cart, the net force on the cart, is going to be the mass times the acceleration. The fact that the cart exerts a force on the horse is irrelevant for the motion of the cart. It's not directly relevant. All that's relevant are the total forces on the cart. So that's the answer you have to give the horse. And then, I whip it or something. Okay, any questions about that? Okay, so we have a lab this week. Did you guys notice that?
Yes.
The handout should be on the Sakai side. So this is acceleration due to gravity, free fall. Gene's working on it. This is the first time Gene has worked on this experiment. Is that right?
Yeah.
Okay. I think.
One time when I graduated.
Yeah, when you took the course. Yeah. Right? Oh no, you had to set up one.
I set it up.
That's right.
Yeah.
So that's good.
We'll get through this.
Yeah. So it's, when is it? Friday? This Friday at 1? Thanks. 13, I have to do a calculation. We say 30. Right.
What room is it in?
It's in
1026.
127. It's called the Basic Physics Lab. It's where the 1121 and 1322 electromagnetism labs. It's just right around the corner, right over here. And there's 2 hours budgeted to it. We should be able to get through. I don't think it's going to be a problem. Do they have to walk away with a graph on from a plotter?
It depends on, I think, how you want to run the reports.
I have to look into that because
We have a printer now, and we've been using USB,
yeah.
like dongles,
Yeah, the problem is these students may not have thumb drives or flash
yeah, thumb
drives.
drives. We're allowed to use it in this case.
Yeah, do you guys have thumb drives? You can tell me, I won't tell anybody.
Sure,
Yeah,
absolutely.
you can use them for Macs, it's okay, it turns out. I was surprised. Yeah, I tried to buy some years ago, 5 years ago or something like that, and somebody said, oh, you can't put those through the purchasing system. And sure enough, it got stopped, but then when I told them it was just for Macs, they said, oh, fine. So I said, great. But anyway, you might want to bring a thumb, if you got a thumb drive, so that you can get this plot. It's off an oscilloscope.
We have,
I have to look at the experiment. I can't
we
remember.
have 5 I think 5 thumb drives specific for that lab.
Oh,
that
right.
connect to
Is this what we did last year? We actually bought some
and a brand new printer to plug it into.
and a brand new printer. Okay, so then they have to borrow them and return them.
We're all in the same lab. You guys are going to be running and collecting data. You just plug it in and walk over and print out what you need to print out. Unless you want it all digital, right? Oh yeah, because we're not dealing
Oh,
with
I
these.
see what you're saying. Okay, sorry, I see.
Or you email them to yourself.
So they just, once they get a printout, they can just include it in their report.
Yeah, I mean, that's
Yeah.
the way they ran it. Or
So-
get a smartphone, take a picture of the screen and email it to yourself.
That's a good point. Okay, so we should be okay. And I think that's going to be, in the past, I think that's the only problem that we had
Yeah.
with this experiment. Okay, so everybody's clear about that, right, the lab? Oh, so here's what Gina and I decided. 5 groups of 3. Now, to be honest with you, we do have more setups. We could have more groups, but it gets really hectic for Gina and me with so many groups. We have to circulate among the groups. So we're going to try now. This is kind of new. We always like to experiment. So 5 groups of 3, you can be thinking about that. And they don't have to be the same group for each experiment, if, for whatever reason. But we're going to have 5 groups of 3. It's 3 students in each group. I don't know how many different ways I can say it. There's, okay, so you guys might want to think about that. Yes?
So when is the second quiz due?
It should be on there. And I think it's
Tuesday.
Tuesday at 3 p.m.
Tuesday.
Yeah.
Yeah, that's bad.
And if you run into a problem, let me know, but it's nice if you respect that deadline. It's just I can get on these things, Okay? And I think homework, we're doing okay. I think everybody's turned in the homework now. And